When we speak of the universe as an illusion, we must be careful not to slide into a careless denial of reality. Physics, at its best, does not tell us that the world is a mirage, but that our everyday picture of it is an approximation, useful, robust, and yet profoundly incomplete. The solid table, the flowing passage of time, the smooth arena of space, these are not lies, but shadows cast by a deeper mathematical structure that does not readily submit to common intuition. Consider space and time themselves. In classical physics, they form a continuous backdrop, a perfectly behaved stage upon which matter performs. Yet modern theory undermines this comforting image. Quantum mechanics refuses to assign definite properties until measurement intervenes, while general relativity bends space and time into a dynamic, malleable geometry. When we attempt to merge these two pillars, the familiar stage dissolves. Continuity fractures, locality becomes suspect, and the very notion of a universal now evaporates. What we experience is not the fundamental script, but a coarse-grained synopsis. This is where the sense of illusion arises. The world we perceive is an emergent description, much like the smooth curve that appears when one steps back from a mosaic of discrete tiles. The curve is not fictitious. It captures something real, but it is not present at the level of the tiles themselves. Similarly, particles, fields, and even spacetime may be effective concepts, arising from a more austere and abstract substratum, perhaps best characterized in purely mathematical terms. Mathematics, in this view, is not merely a language we impose upon nature, it is the architecture from which nature is built. The unreasonable effectiveness of mathematics ceases to be unreasonable if physical reality is, at heart, mathematical. What we call illusion is then the mismatch between the pristine precision of that underlying structure and the evolved cognitive tools with which we apprehend it. Our brains, shaped for survival rather than truth, favor stable objects and linear narratives, even when the universe offers neither. Time provides a particularly striking example. Physics allows us to write down equations that make little distinction between past and future, yet our conscious experience insists on a flowing present. This flow may be no more fundamental than the apparent motion in a sequence of still frames. The illusion is compelling, indispensable to experience, and yet absent from the deepest equations we know. To recognize illusion in this sense is not to succumb to nihilism, but to intellectual humility. It invites us to refine our concepts, to search for descriptions that do not merely comfort intuition, but reveal structure. The universe is not unreal. Rather, our most familiar image of it is provisional, a beautifully serviceable approximation awaiting a deeper, more geometrically truthful account. Our encounter with reality is mediated entirely through perception, and perception is not a transparent window onto the world, but a highly processed construction. Physics does not dismiss this construction as erroneous. Instead, it reveals the layered nature of description. What appears to us as solidity, persistence, and determinacy is remarkably reliable at human scales. Yet this reliability should not be mistaken for fundamentality. The success of everyday intuition is a triumph of evolutionary pragmatism, not a certificate of ontological depth. At the microscopic level, the assumptions that underpin ordinary experience begin to erode. Objects no longer possess definite properties independent of observation, and causality itself becomes statistical rather than absolute. Yet when we return to the macroscopic domain, certainty reasserts itself with overwhelming force. Chairs remain chairs, planets trace predictable paths, and time appears to march steadily forward. This duality invites a misunderstanding. We tend to grant primacy to what feels immediate and downgrade what feels abstract. Physics suggests the opposite ordering may be closer to the truth. The concept of approximation is essential here. An approximation is not a mistake. It is a selective description that captures what matters under specific conditions while discarding deeper complexity. Newtonian mechanics is an approximation of relativistic physics, which in turn may be an approximation of something yet more fundamental. Each layer is internally coherent and empirically successful, yet none is final. Our sensory world occupies a similar status. It is a high-level summary compressing vast amounts of underlying structure into forms that cognition can manage. The illusion then does not consist in believing that the world exists, but in believing that it exists in precisely the way it appears. Solidity emerges from electromagnetic interactions and quantum exclusion, principles, none of which resemble the tactile firmness we experience. Color arises not from intrinsic properties of objects, but from the interaction between light frequencies and neural processing. Even spatial extension may be a derived notion rather than a primitive one. What we perceive is real as experience, but indirect as representation. This distinction has profound implications. It forces us to separate ontology from intuition, and to accept that truth in physics often lies far from what feels natural. The equations that best describe the universe do not resemble the world of immediate experience. They inhabit an abstract domain of symmetries, amplitudes, and geometrical relations. Yet their predictive power is unmatched. The tension between mathematical clarity and experiential familiarity is not a failure of science, but a clue to the stratified nature of reality. Once this is acknowledged, the term illusion loses its pejorative tone. An illusion can be indispensable. Perspective in art is an illusion, yet it conveys spatial relationships with remarkable effectiveness. Similarly, our perceptual world is an illusion shaped to be useful, stable, and navigable. Physics does not ask us to abandon this world, but to recognize its place within a hierarchy of descriptions, where deeper levels may be less accessible to intuition, but more faithful to the underlying structure from which all appearances arise. Classical physics presents space and time as a serene and dependable framework, a silent arena in which events unfold without ambiguity. Space stretches smoothly in all directions, time flows uniformly for all observers, and causes precede effects in an orderly sequence. This picture is so deeply ingrained that it feels less like a theory and more like common sense. Yet physics has taught us with increasing insistence that this apparent stability is an artifact of scale rather than a fundamental feature of the universe. General relativity delivers the first major rupture. Space and time are no longer passive containers but dynamic entities, responsive to matter and energy. Mass curves space-time, and this curvature dictates motion. The separation between space and time dissolves into a single geometric structure, undermining the notion of an absolute temporal order. Events that are simultaneous for one observer may not be so for another, and the idea of a universal present loses any precise meaning. Already, the classical picture has begun to fracture. Quantum mechanics pushes the disintegration further. At sufficiently small scales, the concept of a well-defined location becomes problematic. Particles cannot be assigned precise positions and momenta simultaneously, and interactions appear inherently non-local in their correlations. The smooth continuity assumed by classical spacetime becomes increasingly difficult to justify. When quantum theory is applied to fields rather than particles, the vacuum itself seethes with activity, far removed from the idea of empty space as a neutral backdrop. The true crisis emerges when these two frameworks are forced together. Attempts to quantize spacetime reveal profound inconsistencies, suggesting that spacetime is a continuous, manifold cannot survive at the most fundamental level. Many approaches to quantum gravity imply that spacetime is emergent, assembled from more primitive, non-spatial elements. In such pictures, distance, duration, and even dimensionality may arise only approximately, much as temperature emerges from the collective behavior of molecules rather than existing at the level of individual particles. Locality, long regarded as sacrosanct, also comes under scrutiny. If spacetime itself is emergent, then the notion that influences propagate strictly through neighboring points may be an effective rule rather than a fundamental one. Quantum entanglement hints at this possibility, revealing correlations that defy classical spatial separation without transmitting signals in any conventional sense. These phenomena do not violate causality, but they do challenge the idea that spacetime geometry fully captures the structure of physical relations. What we call space and time, then, may be closer to thermodynamic variables than to fundamental constituents. They describe regularities that hold when vast numbers of underlying degrees of freedom are averaged together. At human scales, this averaging is so effective that spacetime appears smooth and absolute, masking the intricate architecture beneath. Physics does not suggest that space and time are unreal, but that their apparent simplicity is the result of emergence, not evidence of primacy. The idea of emergence provides a bridge between the deep abstractions of fundamental physics and the tangible world of experience. It allows us to understand how complex, stable structures can arise from constituents that bear little resemblance to the phenomena they collectively produce. In this sense, emergence is not a philosophical embellishment, but a necessity imposed by the behavior of nature itself. Without it, the gap between microscopic laws and macroscopic reality would remain unbridgeable. A familiar illustration comes from condensed matter physics. Individual atoms obey quantum rules that are subtle, probabilistic, and often counterintuitive. Yet when arranged in vast numbers, they give rise to solids with rigidity, liquids with flow, and phases with sharply defined properties. None of these macroscopic characteristics can be attributed to a single atom in isolation. They emerge only when collective behavior is considered, and they do so with remarkable robustness. A crystal does not lose its symmetry because one atom is misplaced, just as a fluid does not cease to flow because of a minor perturbation. This robustness is central to why emergent phenomena appear fundamental to us. The higher-level description becomes largely insensitive to the fine details of the underlying layer. Temperature does not require knowledge of individual molecular trajectories, and pressure does not depend on the identity of specific particles. In the same way, space-time geometry and particle-like excitations may be effective summaries of deeper degrees of freedom, capturing what matters while suppressing inaccessible complexity. When applied to the fabric of reality itself, emergence takes on a more radical significance. If space-time, matter, and even causality arise from underlying structures, then the world we directly perceive is not a faithful image of the fundamental level. It is an interpretive layer, shaped by stability and regularity rather than microscopic truth. The illusion lies not in the existence of this layer, but in mistaking it for the foundation upon which everything else rests. This perspective alters how we think about reductionism. Explaining a phenomenon in terms of more basic constituents does not necessarily diminish its reality. A rainbow is no less real because it can be explained through optics, nor is consciousness rendered illusory by its neural basis. Emergent phenomena possess their own legitimacy, governed by laws that are autonomous within their domain. The danger arises only when we assume that what is emergent must be epiphenomenal or dispensable. In physics, this autonomy is both practical and conceptual. We routinely employ theories that are known to be effective rather than fundamental, because they capture the relevant behavior with extraordinary accuracy. The illusion of fundamentality is a byproduct of success. When a description works across vast ranges of conditions, it acquires an air of inevitability. Yet history shows that even the most entrenched frameworks can be subsumed within deeper ones. To accept emergence as central is to accept a layered universe, where each level has its own vocabulary, laws, and explanatory power. The world of experience occupies one such level, exquisitely tuned to human perception and action. Beneath it lies a domain that may be far removed from intuition, yet it is from this hidden architecture that the apparent solidity and coherence of reality arise. The striking success of mathematics in describing the physical world has long been treated as a fortunate coincidence, a convenient alignment between abstract symbols and empirical observation. Yet, as physics has progressed, this coincidence has grown increasingly difficult to dismiss as accidental. The deeper our theories reach, the more they rely on mathematical structures that appear to possess an existence and coherence independent of human invention. This invites the unsettling possibility that mathematics is not merely a descriptive tool, but the very substance from which physical reality is composed. In fundamental physics, equations do not merely summarize experimental results, they constrain what can exist. Symmetry principles dictate conservation laws, geometric relations define gravitational dynamics, and abstract spaces encode the behavior of quantum states. Often, these mathematical requirements lead to predictions that seem detached from physical intuition, yet are later confirmed with remarkable precision. The physical world appears to conform to mathematical necessity rather than the other way around, as though reality were obliged to obey rules written in an abstract, non-empirical domain. This perspective challenges the common distinction between map and territory. In everyday life, models are approximations, useful but disposable. In fundamental physics, however, the model often outlasts any particular interpretation. When intuitive pictures fail, the mathematics remains intact, continuing to generate accurate predictions, even as our conceptual understanding falters. It is the equations, not the imagery we attach to them, that carry explanatory weight. If mathematics is primary, then physical entities may be secondary manifestations of mathematical relations. Particles become excitations of fields. Fields become representations of symmetry groups. And space-time becomes a geometric structure defined by invariant quantities. At each step, the substance of reality grows more abstract, moving further away from sensory qualities and closer to pure relational form. What we perceive as objects may be intersections of mathematical constraints rather than self-subsisting things. This does not imply that mathematics is invented by humans in the same sense that tools or languages are invented. Rather, it suggests that mathematical structures are discovered, much as physical laws are. Different mathematical systems possess internal consistency and necessity regardless of whether they are ever applied to the physical world. Physics appears to select a subset of these structures, those capable of sustaining stable patterns and observers, and manifests them as the universe we inhabit. From this viewpoint, the illusion lies in attributing primacy to the tangible. The solidity of matter, the continuity of space, and the flow of time are not fundamental ingredients, but emergent expressions of deeper mathematical order. Our confidence in the physical stems from its immediacy, yet immediacy is no guide to depth. The most real aspects of the universe may be those least accessible to the senses, residing instead in abstract relationships that can only be apprehended through mathematical reasoning. Accepting this reverses a deeply rooted intuition. Instead of mathematics being a shadow cast by the physical world becomes a projection of mathematics into a form compatible with perception. Reality on this account is not made of substance in the classical sense, but of structure, and it is this structure that persists when familiar images dissolve under closer scrutiny. Human intuition feels authoritative because it is immediate and effortless, yet its reliability is narrowly scoped. The cognitive frameworks through which we interpret the world were shaped not to uncover fundamental truth, but to ensure survival within a limited environment. As a result, our intuitive grasp of reality is tuned to medium-sized objects moving at modest speeds, interacting through forces that are stable and predictable. Physics, however, operates far outside this comfort zone, and it is precisely there that intuition begins to mislead. When confronted with quantum phenomena, intuition repeatedly fails. We expect objects to possess definite properties, to follow continuous trajectories, and to exist independently of observation. None of these expectations survive careful examination at microscopic scales. Superposition, uncertainty, and entanglement defy classical reasoning, yet they are not anomalies or approximations. They are the core features of how nature behaves when stripped of macroscopic averaging. The discomfort they provoke is not evidence of their falsity, but of the limitations of our evolved conceptual habits. Relativity delivers a similar lesson. Intuition insists on absolute time and rigid spatial separation, yet both dissolve under relativistic analysis. Time dilates, lengths contract, and simultaneity becomes observer-dependent. These effects are not philosophical curiosities, but measurable consequences of well-tested theory. The fact that they feel implausible only underscores how poorly intuition scales beyond everyday conditions. This mismatch between intuition and reality often leads to resistance. There is a temptation to search for hidden variables, preferred frames, or comforting narratives that restore classical sensibilities. While such efforts can be intellectually valuable, they are frequently motivated by psychological unease rather than empirical necessity. Physics has progressed by resisting this temptation, allowing mathematical consistency and experimental evidence to override what feels natural. The danger of overvaluing intuition lies not merely in misunderstanding specific theories, but in mistaking familiarity for truth. Concepts that align with everyday experience acquire an unwarranted sense of inevitability. Conversely, abstract ideas are dismissed as artificial or unreal, even when they are the only frameworks capable of making accurate predictions. This inversion of credibility places the burden of justification on the very theories that have proven most successful. Recognizing the limits of intuition does not require abandoning it altogether. At higher levels of description, intuition remains indispensable. Engineers, biologists, and astronomers rely on intuitive models that work extraordinarily well within their domains. The mistake is to assume that these models retain their authority at the most fundamental level. Physics demands a willingness to let intuition be trained, extended, or even replaced by mathematical insight. The deepest theories of nature do not aim to be comforting. They aim to be coherent, predictive, and universal. If they conflict with intuition, it is intuition that must yield. The illusion is not that the universe behaves strangely, but that it ought to behave in ways that align with human expectation, despite those expectations being shaped by a very narrow slice of reality. Time occupies a peculiar position in our understanding of reality. It feels immediate and undeniable, flowing from past to future with a sense of inevitability that structures memory, expectation, and identity. This apparent flow is so central to conscious experience that it is often taken as the most fundamental feature of the universe. Yet when examined through the lens of physics, time behaves in ways that sit uneasily with this deeply ingrained intuition. In the fundamental equations that govern physical law, time rarely plays a privileged role. Many of the most successful theories are time-symmetric, making no intrinsic distinction between past and future. The equations remain valid if the direction of time is reversed, suggesting that the laws themselves do not encode a preferred temporal orientation. This stands in stark contrast to human experience, where the past feels fixed, the future open, and the present uniquely real. The sensation of temporal flow may therefore arise not from the structure of the universe, but from the structure of cognition. Memory records past states, anticipation projects future possibilities, and consciousness stitches these together into a narrative of becoming. From this perspective, the present moment is not a fundamental slice of reality, but a construct, generated by information processing. Physics offers no clear place for this privilege now, and its absence is telling. Relativity deepens the puzzle. Different observers, moving relative to one another, do not agree on which events are simultaneous. What one observer regards as happening now, another may place in the past or future. There is no observer-independent present that can be singled out as objectively real. Instead, space-time presents itself as a four-dimensional structure in which all events coexist, ordered but not animated by any universal flow. This block-like view of time is often met with resistance, not because it lacks empirical support, but because it conflicts with lived experience. Yet conflict with experience does not imply error. The perception of motion in cinema arises from a sequence of static frames, none of which move. Similarly, the impression of temporal passage may emerge from correlations between physical states without time itself flowing at a fundamental level. Thermodynamics introduces an apparent arrow of time through the growth of entropy, but this arrow reflects statistical behavior rather than a basic temporal asymmetry. Entropy increases because of special initial conditions, not because time itself has a built-in direction. The distinction between past and future may therefore be a macroscopic phenomenon, arising from improbability and information loss, rather than a feature written into the fabric of reality. If the flow of time is emergent, then its reality is contextual rather than absolute. It is real for creatures embedded in complex systems, processing information in irreversible ways. It organizes experience and gives coherence to action. Yet it may have no counterpart in the deepest description of the universe. The unsettling implicatio. N is not that time is unreal, but that its most familiar aspect, the sense of passage, is a cognitive artifact arising from our particular mode of existence.